So a very good morning to you guys, and today I finally found time to make the video on NMR spectroscopy, which I had told in my earlier videos as well is my favorite topic, right? And a lot of you had requested me earlier also in fact you were requesting me from a very long time that you need a video on NMR spectroscopy. So today I decided that for the first video on this whiteboard is going to be about NMR spectroscopy. Sorry, not whiteboard, green board, right? Now I've actually filmed the whole video on NMR spectroscopy, a 30-40 minute long video, and I was not satisfied with the content, so I'm filming it again. Hopefully this time I would be satisfied with what I have taught, right? Because NMR spectroscopy is my favorite topic and I want to teach it in the best possible manner that I can, right? I do not want to give you second class or third class information. I want to give a good lecture on NMR spectroscopy. Okay, so now let's discuss NMR spectroscopy. NMR spectroscopy stands for your nuclear magnetic resonance spectroscopy. So it has got something to do with the nucleus, because nuclear, magnetic, it has something to do with the magnets, and resonance means there's some kind of resonance that is going to take place. All right, so what exactly is this NMR spectroscopy? Why do we need to study it? So first of all, it has become an indispensable tool for an organic chemist. Okay, our organic chemist cannot do anything without an NMR spectrometer, right? Or the instrumentation that is required. And secondly, it's quite an easy technique because for structural elucidation. Okay, so right now we also have single crystal XRD, but for single crystal XRD we need to have a instrument. Okay, first of all we need to make a crystal, and crystallizing each and every compound sometimes becomes very tedious and very difficult. On the other hand, on NMR spectroscopy we simply need to dissolve it in a particular solvent, a deuterated solvent. Okay, now I do not want to touch this aspect of what is a deuterated solvent, but for now I'll tell you, like chloroform is there. Chloroform is as a solvent and the formula is CHCl3 for chloroform. But if I use, instead of hydrogen in chloroform, I use deuterium, then it's called deuterated chloroform or CdCl3. Okay, so that is a deuterated form of chloroform. And why do we need to use deuterated solvents for NMR spectroscopy? That I will discuss in some other video on NMR spectroscopy. Right now that is not what we are going to study today. Today we are going to discuss each and every topic and understand conceptually. You must have heard of terms like downfield, upfield, and what exactly is this, and how do these terms correlate with NMR spectroscopy? That I'm going to discuss, because nobody tells you that. All right, so so it is a very important tool. That's all you need to know right now. Sometime in your life, if you become a researcher, definitely you'll have to use NMR spectrometer, that I can guarantee. If you are working with electrochemistry or something else, that's a different thing, but some or the other way you'll have to work with an NMR spectrometer, right? Okay, so one essential condition that you need to know, because you are talking about nuclear magnetic resonance, so it has something to do with the nuclear spin. And so basically your nuclear spin is basically the factor which plays a key role. Okay, now the one essential condition for a nucleus to be NMR active is that it should have a non-zero spin. Okay, so one essential condition that should be there with any atom or any nucleus is that it should have non-zero spin, non-zero nuclear spin, right? So for example, if I talk about hydrogen, or we commonly do 1H NMR. Okay, so the most common form of NMR spectroscopy is the NMR of proton or 1H. Okay, hydrogen atom. So that's why it's sometimes called as proton NMR, because a hydrogen atom only consists of one proton, so that's why it's commonly called as proton NMR. You can also call it 1H NMR, so don't get confused over there. So our hydrogen has a spin of half. Okay, and if you want to know how do we calculate the nuclear spin, then you need to watch a video on calculation of nuclear spin, which I've already done a whole dedicated video. You can find the link over here, calculation of nuclear spin, right? So you can calculate the nuclear spin of each and every atom, and I've shown you how in that particular video. But right now our essential condition is that the nucleus should have a non-zero spin, and I'll tell you one tool by which you can find out whether the atom has a non-zero spin or not. So any nucleus which has an even mass number and an even atomic number will have zero spin. For example, if I talk about our carbon nucleus, the 12C6, so it has a mass number 12 which is even and has an atomic number 6 which is even. So since both the things are even, this has 0 spin. Okay, so this is not NMR active. Similarly, if I talk about oxygen, 1608, okay, again even at mass number and even atomic number, so again it's not NMR active. 0, non-zero, it has a 0 spin, so it's not NMR active. Whereas our proton or hydrogen has a spin of half. Similarly, deuterium has a spin of 1. Fluorine 19F has a spin of half. Okay, so we have this is the basic thing that you need to understand, that if the atomic number is even and the mass number is even, then it's not NMR active, and that's a good thing, because there will be no interference from our carbon and oxygen in your, if you are taking out NMR spectroscopy of organic molecules. So that's a very good thing for us. But on the other hand, if I talk about 13C6, this has a spin of half and it's NMR active. Okay, so this is the less abundant isotope of carbon, and this is NMR active because it has a odd mass number, right? So the essential condition is that it should have a non-zero nuclear spin. That's all we are concerned with for NMR spectroscopy. So that nucleus will be NMR active, which has a non-zero nuclear spin, right? Okay, so first of all, you must be wondering what exactly is this spin. Okay, does the nucleus spin, or what exactly is this spin? So this is a very good question and a very complex question, because for a simplicity we say nuclear spin, but that is not how things work in a quantum mechanical way, because nucleus and your protons, your electrons, your bosons, your fermions, your leptons, all of these are subatomic particles, and they are all governed by the laws of quantum mechanics. So spin is a very simple, or it's a simplification of the term. Okay, that's not what exactly happens, but for our simplicity, and we'll not dive into particle physics, because that's in itself is a very complex topic, and not many people in the world understand particle physics. So for our convenience, we'll just keep it to spin only, that the nucleus is spinning. Okay, so our spinning nucleus, so what exactly happens in NMR spectroscopy, that we are going to discuss. Okay, right, so a spinning nucleus, it generates a spinning charge, you can say. So nucleus is charged, so a spinning nucleus, it has a magnetic moment, or magnetic, yeah, you can say a magnetic moment or a magnetic field associated with it. Okay, but in the presence of, if there's no external magnetic field present, then we'll have only one form of magnetic field. But let's say, or only one form of energy. Okay, if there's no external magnetic field, we'll only have one form of energy. Right now I'm talking about hydrogen or proton NMR only. Okay, but once we provide some external magnetic field, what happens is it splits into two energy levels. Okay, and why does it split into two energy levels? Because of quantum mechanical restrictions. Okay, because of quantum mechanical restrictions, it splits into two energy levels. So it depends from nucleus to nucleus. For example, if I talk about chlorine has a spin of 3/2. One of the isotopes of chlorine, I don't remember which isotope, has a spin of 3/2. So this splits into 4 energy levels in the presence of an external magnetic field. But our hydrogen, or any nucleus with spin half, it splits into only two energy levels, and that formula is basically, or that restriction, the quantum mechanical restriction, is 2I+1. Okay, where our I is the spin. So for example, I told you for hydrogen we have spin half, right? So 2 into half plus 1, so this gives us 2 energy levels. So that's why we have 2 energy levels. If I talk about chlorine, if I replace this I by 3/2, so 2 into 3/2, so this becomes 3+1. So that's why it gets split into 4 energy levels. So this formula comes because of quantum mechanics. So due to quantum mechanical restrictions, it gets split into 2 energy levels if I am talking about nucleus with spin half, and in particular hydrogen. So it gets split into 2 energy levels. Okay, it gets split into 2 energy levels, and let's say those 2 energy levels are, just let me rub this off. Right, so we have some energy which is degenerate when we don't have an external magnetic field. As soon as we apply external magnetic field, what happens is it gets split into 2 energy levels, let's say beta, and the other one, let's say alpha. This is in presence of our external magnetic field, let's say B0. So in presence of external magnetic field, this energy level gets split into alpha and beta, that is two energy levels. Okay, so this one is of lower energy level and this one is of higher energy level. So why does this happen? It's very simple. If you have seen a compass, the compass aligns itself to the magnetic field of the earth. Similarly, when an external magnetic field is applied, your nucleus, it is also acting as a magnet, and it aligns itself either with the magnetic field or against the magnetic field. So let's say this is with the magnetic field, it aligns with the magnetic field. I'll write down over here aligns, and this one over here, it is not aligned. Okay, let's say it's not aligned, that's why it's of higher energy level. To understand it in a simpler manner, let's say we have this north pole and this south pole of the magnet. Okay, and we have the nucleus. So the nucleus is also acting as a tiny bar magnet, and so the nucleus, if this is the case, that is the south is towards the north and the north is towards the south, it is aligned with the field. Okay, this is a stable energy form, and let's say this energy state is alpha. Okay, let's say this energy state is alpha. The other form could be that we have the two poles of the magnet, north and south of the external magnet, and now what we have is the south towards the south and north towards the north. So this north and north will repel and this south and south will repel. So this is the higher energy form. Okay, so you can understand it in a simple way like that. So because of this, one energy state is of lower energy and the other one is of higher energy. Now this gap between the energy levels alpha and beta, this is called delta E. Let's say this energy gap is delta E. Okay, this energy gap is delta E, and this delta E is actually equal to gamma h by 2 pi b naught. So this delta E that we have, it depends on your gamma h by 2 pi b naught, where h is your Planck's constant, 2 pi you know what exactly it is, b naught is our external magnetic field, and gamma over here is something called as a gyromagnetic ratio, which depends on the nucleus. So if you are talking about hydrogen, it will have a different gyromagnetic ratio. If you are talking about fluorine, it will have a different gyromagnetic ratio. So it depends from atom to atom or nucleus to nucleus. So it depends on the nucleus that what will be the gyromagnetic ratio. Okay, gyromagnetic ratio. For those of you who don't understand, I'll just write down the spelling. Gyromagnetic ratio. Okay, it's called the gyromagnetic ratio. In some books you will also see magneto-gyro ratio, something like that. So it's the same thing. So this is the gyromagnetic ratio and depends from nucleus to nucleus. So you cannot change that. The only thing you can change over here is your B naught, that is your magnetic field. So that is the only thing that you can change, the external magnetic field. And you can see that this delta E is directly proportional to B naught. This delta E is directly proportional to B naught. What does that mean is that if we increase the magnetic field, the energy gap between the alpha and beta form will increase. So let's say if I plot on the x-axis your B naught, so you can see as we are increasing the magnetic field from this point to this point, the energy gap is continuously increasing. So as the magnetic field, external magnetic field applied increases, the gap between the alpha form and the beta form increases. So this is a very important thing that you need to understand, and a lot of questions are asked from this particular concept only. In fact, if I'm not wrong, in CSI Net there was a question, a 4-marker, that what changes the energy gap between the alpha and beta form, or how to increase the energy gap between the alpha and beta form. By applying a higher external magnetic field, we can increase this gap between the alpha and the beta form. Now why do we need to increase the gap between the alpha and the beta form? So all of you know, if you have seen my spectroscopy videos, the intensity or the clarity of a NMR, let's say NMR spectra, or any spectroscopic, if you are doing any kind of spectroscopy, the clarity of that spectra, it depends on the population difference. The higher the population difference in the lower energy state, or from where the excitation is taking place, the greater will be the better will be the clarity of the spectra. Okay, you can think of it as a camera clarity. So if you're using a 2 megapixel camera and if you're using a 20 megapixel camera, there will be some clarity in the picture. Similarly over here, if the population in the lower energy state is more, or the population difference between the alpha state and the beta state is more, the NMR spectra is going to be better and more clear. Okay, so if we increase this energy gap between the alpha form and the beta form, what is going to happen is the population difference between this alpha state and beta state, the nuclei in the alpha state and the nuclei in the beta state. Some nuclei will be there in beta, some nuclei will be there in alpha. So if we increase this energy gap, the population difference will increase and our NMR spectra will be more clear. It will be very you can see more things in the NMR spectra. So that is why increasing this energy gap is essential, and that we can do with the help of a higher external magnetic field. That's why today you might have seen NMR instruments called, earlier in 1960s 1970s we used to use a 60 megahertz NMR, we used to use a 60 megahertz NMR instrument, right? But nowadays we use close to 400. In common labs, in your common universities, you will see a 400 megahertz NMR spectrometer, but in very high-end laboratories you will see 800 megahertz NMR spectrometer as well. In fact, 1000 also, 1200 also, right? So the greater this frequency, the better the NMR. Okay, and why don't we call it in the field of why do we say megahertz in the form of frequency? That I'll talk about later, that how come radio frequency plays a role, or in fact I'll just talk about it right now. So this delta E is equal to R H mu, right? Energy is equal to the Planck's constant into the frequency. Now to carry out resonance, we need some frequency V which can match this energy gap, or some radio frequency that we supply in the NMR instrument. So in the NMR instrument we have a very high, strong, superconducting magnet you can think of, and we have a radio frequency source. So what does this radio frequency source do is, it provides some frequency. Once this frequency matches the energy difference between the alpha state and the beta state, resonance takes place. Some of the nuclei from the lower or the ground state, they go into the excited state, you can think of it that way, and once they go to the higher energy state, then relaxation takes place, and I'll talk about relaxation in detail in some other video, right? In this video I'm just talking about the basic how NMR spectroscopy works. So it goes and gets excited to the beta state, and once from the beta state it comes back to the alpha state via relaxation. It emits some radiation which the detector detects. Okay, so this is the whole principle. Now if this energy difference between the alpha and the beta state is more, that means we need to provide a higher frequency, because delta E is equal to H mu, or from here the energy difference is directly proportional to frequency. So if the energy difference increases, we'll have to supply a higher frequency radiation. Okay, so this is a very important relation that you have to understand. This is the crux of your NMR spectroscopy. If you increase the magnetic field, the energy gap increases. If the energy gap increases, in order to carry out the resonance, you'll have to provide a higher energy frequency source. So automatically, if we are doing 60 megahertz NMR instrument, we require a magnetic field of 1.41 Tesla. Okay, what I mean by, if we are applying a magnetic field of 1.41 Tesla, this energy gap can be fulfilled by an instrument of 60 megahertz. Okay, this is what I mean. So if I'm providing energy of 1.41, if I'm providing a magnetic field, external magnetic field of 1.41 Tesla, then I require to do resonance, to carry out resonance, I require a radiation of 60 megahertz. And why only 60? That I'll discuss. Okay, why only 60? Why not 61? Why not 59? Because all the protons in a you can say molecule, they are in different environments. So they have different radiations at which resonance occurs. So why are we specifying 60 megahertz? That I'll discuss. I know you must be having that doubt, but I'm going to discuss that doubt as well. So 1.41 Tesla, 60 megahertz. As I increase this magnetic field, if I increase the external magnetic field, I'm not remembering the exact term, but if this is somewhere around 10 Tesla, okay, then let's say we'll have a frequency of 800 megahertz. So it automatically increases. So if we say 800 megahertz, automatically we'll require a higher magnetic field, a higher external magnetic field. So that's why we prefer to talk in terms of frequency, radio frequency, rather than in terms of magnetic field, because they go hand in hand. If I'm providing, let's say, simply I'm using only 1.41 Tesla magnetic field, I'm using external magnetic field of 1.41 Tesla, so that means I require 60 megahertz worth of radio frequency to carry out the resonance. But in case I'm applying external magnetic field of 1.41 Tesla and I'm giving the external frequency, the radio frequency of 800 megahertz, the resonance will not take place because I'm providing a higher energy and the gap between them is only worth 60 megahertz, whereas I'm providing 800 megahertz. So resonance will not take place. Resonance will only take place if this gap matches. That's how resonance takes place. That is, this frequency is equal to the energy gap. If this frequency is more, your resonance will not happen. Similarly, if this delta E is more and your frequency is less, resonance will not happen. That means now if I am using 10 Tesla worth of magnetic field, but I am only providing 60 megahertz, even then the resonance will not take place and will not get a spectra. So the only way that it works is both go hand in hand. Both of these things go hand in hand. Alright? Now, okay, so I think I should carry a piece of paper with me where I should write the topics, because before the video I tend to remember all the topics, but sometimes I just forget one topic before the other. So I think next time onwards I'll have a piece of paper where I write down all the topics that I need to teach. Alright? Right? Right, anyway, so this is also a different aspect to look at it. This is one aspect that I've taught on how we can, look at the principles of NMR spectroscopy, but there's a different aspect or a different way that we can look at it, which I prefer. Okay, and now what is the different aspect that we are going to discuss? So I really hope that you are liking this lecture, and in case you do, please, I would love to hear it from you guys. I know you don't like, many of you don't comment and you watch it and you like it, but I really prefer if this time you can actually comment and let me know how you found this video. Only this time. I'm not telling you to comment on all my videos, but just for this time, because this topic is really important to me, so you can just tell me, give me a feedback on how I taught it, and I really appreciate it. Okay. Right, so the other aspect that we need to understand is you have to think of a spinning top. Okay, a spinning top, or what we call as a lattu. Okay, you must have heard of lattu, right? We used to play with it in our childhood, and you must have played with Beyblades, right? Beyblades was there was a lot of craze 10 years back of Pokemons and Beyblades, and I was a part of that craze. And spinning top, lattu, you must have been playing with lattu as well, right? So what happens in a lattu is that we have one axis of rotation, but the lattu does not rotate simply in a straight line. Okay, it does not rotate simply, it rotates like this. It rotates like this. Okay, if you're not able to understand this, think of it this way, that when a lattu or a spinning top is about to fall, okay, when a lattu or a spinning top is about to fall, you must have seen it starts to wobble. It starts to wobble when it's about to fall, because it's rotating like this, it starts to wobble. So when it's actually rotating at a very high speed, it does not rotate in a circle, it rotates in the form of a cone. It makes a cone. Okay, so if I draw it, I'm not very good at drawing, but let's say this is the center. Okay, let's say this is the center. Yeah, so this is the center where it's rotating, but it does not rotate in a straight line, in a form of a circle. It makes like a cone shaped geometry. Okay, so this is how it's rotating. Now this geometry that is rotating, you can think of nucleus also rotating like this. If I talk about, let's say if I'm talking about hydrogen or proton NMR, you can think of the hydrogen nucleus also rotating like this. Okay, and this rotation is called your Larmor precession. This rotation is called your Larmor precession, or commonly it's also called precessional frequency or Larmor precession. So this movement of your nucleus is called your Larmor precession, and let's say it's rotating with some frequency called omega. Okay, it's rotating with some frequency called omega. So this is this frequency of its rotation is called omega. Okay, now I'm telling you, we have to understand it in a different way, right? Again, we'll provide some radio frequency h mu. For the resonance to take place, this h mu should be equal to your h omega. So your h mu should be equal to h omega, only then your resonance will take place. Okay, so your Larmor precession should be equal to your radio frequency, only then the resonance will take place and it will go to a higher energy state, come back, emit some radio frequency which the detector will detect. Now this frequency, so this is, like I told you, that was another way that I discussed just a few minutes back of looking at your NMR spectroscopy, and this is the other way which I prefer because you can have a more conceptual understanding with this way. Okay, so this precessional frequency again depends on your magnetic field. So this precessional frequency depends on your magnetic field. If we apply a higher magnetic field, this precessional frequency or your Larmor precession is going to increase. Okay, so if we apply a higher magnetic field, it will start to precess even faster. So let's say I'm applying a magnetic field B0. So the higher this external magnetic field, the faster it will precess, and the faster it precesses, the higher electromagnetic radiation we'll have to provide in order to carry out resonance. So the faster it's rotating, the faster it's precessing, the faster, the more this value is also going to increase if it moves faster. And if this value increases, then to carry out resonance, we'll also have to increase this value. So that means we'll have to provide a higher radio frequency source, right? Okay, so this is the basis of NMR spectroscopy. Now what happens is, the electron is there in a nucleus, right? A nucleus always has an electron surrounding it. Now the electron also has some magnetic field associated with it. It has a tiny magnetic moment associated with it. A spinning electron also has some kind of magnetic moment associated with it. Okay, now what does this magnetic moment do is, this magnetic field of the electron or the magnetic moment of the electron, it shields the nucleus. Now this is very, very important to understand. This is the crux of NMR spectroscopy. The electron, it shields your nucleus. Okay, let's say this is your nucleus precessing and it has some electrons surrounding this nucleus. The electron has its magnetic field and it will shield the nucleus from the external magnetic field. It will shield means basically it will try and protect your nucleus from the external magnetic field. Okay, it will try and protect. So that means the electron will, you have to understand this very, very carefully. I'm repeating it. I'll repeat it 2 or 3 times again so that you understand it fully. The electron has some magnetic field associated with it. Okay, the electron has some magnetic field associated with it. The magnetic field will protect the nucleus from the external magnetic field. It will not be able to fully protect because electron has a very, very small magnetic field as compared to the external magnetic field, but still it has some small magnetic field, so it will make a small difference. So that means, let's say if I'm applying 1 Tesla of magnetic field. So this is a hypothetical example. Okay, I do not know the actual values, but let's say I'm applying a 1 Tesla magnetic field and the electron has 0.1 Tesla magnetic field of its own. So the nucleus is actually observing only 1 Tesla minus 0.1 Tesla. Okay, just a second. Yeah, so the nucleus is only observing 0.1 Tesla minus 0.1 Tesla, which comes out to be equal to 0.9 Tesla. So that means the electron, the effective nuclear charge or the effective magnetic field, the effective magnetic field which is seen by this nucleus is equal to 0.1 Tesla. We are applying a magnetic field, external magnetic field of 1 Tesla, but because of 0.1 Tesla of magnetic field of the electron, the effective magnetic field that is seen by this nucleus is 0.9 Tesla. Okay, now this is the best part about NMR spectroscopy. So that's why in different chemical environments we get different chemical shifts, because let's say now I'll correlate it with actual molecules. Okay, now I'll correlate it with actual molecules. So let's say we have aniline. Okay, let's say we have aniline, and on the other hand we have nitrobenzene. Now all of you know NH2 is an electron donating group. NH2 is an electron donating group and NO2 is an electron withdrawing group. So let's say we are talking about this hydrogen. Okay, let's say we are talking about these hydrogens. this NH2 is going to donate electrons. It's an ortho-para directing group, so it is going to donate electrons and it's going to increase the electron density at the ortho position and at the para position. Because of this increase in electron density, what happens is the number of electrons surrounding this hydrogen, it increases. That means there will be more shielding because there are more number of electrons. There is more electron density, so there is going to be more shielding. So what I told you, the effective nuclear, let's say in this case the effective nuclear charge, effective magnetic field seen by this hydrogen is 0.9 Tesla in this case, in the case of aniline. In case of nitro, what will happen is this NO2 will withdraw electrons from the ortho and para position. So what happens to this hydrogen is the electron density close to this hydrogen decreases. And because the electron density decreases, the shielding that was earlier provided by the electron that I was talking about, 0.1 Tesla, that will decrease because this is having a higher electron density. Aniline is having a higher electron density, so it is having more shielding. More number of electrons means more number of magnetic field associated with those electrons. That means the shielding will be greater. So the magnetic field seen is 0.9 Tesla by the nucleus. In case of nitro, it's electron withdrawing group, so the electron density decreases. That means the shielding is less. Because the shielding is less, if we are applying, let's say 1 Tesla, in case of nitrobenzene I'm talking about, this was in case of NH2. In case of nitrobenzene, what will happen is shielding will be less. So let's say it's around 0.05 Tesla only. Instead of 0.1 Tesla, it's 0.05 Tesla. So now the nuclear charge that is seen is 0.95 Tesla. So now why am I saying nuclear charge again and again? The magnetic field that is seen by this hydrogen is 0.95 Tesla. Okay. So now the magnetic field seen is 0.95 Tesla. Now what difference does it make? Now let's correlate. It's very, very interesting, right? So in this case, this hydrogen is experiencing 0.9 Tesla, and I told you that if it's experiencing 0.9 Tesla, it will, let's say, rotate by h omega 0.9. Let's say h omega 0.9. Okay, so that means it will require a radiation of h mu 0.9. So if we provide a radiation of mu 0.9, the resonance will take place for this particular hydrogen. But let's say if I'm talking about NO2. In NO2, what will happen is experiencing 0.95 Tesla. So that means it's precessing, the frequency of the precession of this particular hydrogen is greater. Now this one is precessing at 0.95 Tesla. It is seeing a higher external magnetic field. Because this one is seeing a higher external magnetic field, it will precess faster as compared to the NH2 proton. As compared to this aniline proton, this one is the nitro proton will precess faster because it is seeing a NMR, it's seeing a nuclear, you can say a magnetic field of 0.9 Tesla, the aniline proton, whereas the nitro proton is seeing the magnetic field of 0.95 Tesla. Since this one is seeing a greater magnetic field, I told you if the magnetic field is greater, it will precess faster. Since it's precessing faster, this h omega value will increase, and since this h omega value will increase, we'll have to provide a higher radio frequency source. So if we provide a higher radio frequency source, so it will resonate at 0.95. So it will resonate at a higher radio frequency. This is how there is a difference between the two hydrogens due to the chemical environment, and this is the basis of your NMR spectroscopy, right? So this is the crux of the whole matter. This is how it depends. This is how the whole thing works. And whoever went ahead with this concept and developed this concept, sorry, I'm forgetting the name, he got a Nobel Prize as well. He was a physicist. Amazing brains. This is called, this is something mind-blowing, right? How he came up with it, how he thought about it, it's mind-blowing, right? So this is the whole crux of your NMR spectroscopy. Now we say we provide a radio frequency of 800 megahertz or 60 megahertz or 300 megahertz, 400 megahertz. So if this radio frequency is constant, then how come if this is resonating at some different radio frequency and this one is resonating at a different radio frequency, how come if we apply 60 megahertz only or 400 megahertz only or 300 megahertz only, the resonance will take place? How is this happening? What are we varying so that if we are keeping a constant radio frequency, what exactly is happening? Nobody understands that as of now, or nobody teaches that as of now, that what exactly is happening. We are saying we are applying a constant radio frequency, whereas we are saying this will resonate at a different radio frequency and this will resonate at a different radio frequency. But if we are keeping the radio frequency constant, then how are things different? That part we are going to discuss in our next video, right? So I hope you really liked this video, and if you did, please give it a big thumbs up. Do not forget to comment. Even if you don't comment on any of my videos and you still like the content, just comment today, right? I'll really appreciate it. And do not forget to subscribe to my channel and share it with your friends. Thank you so much for watching.